In this video, I'm going to talk about the list class, which is built into the C# language. Lists are very useful. I find myself using them a lot more than I use arrays. So let's just talk about lists and their advantages. And also, they do have some disadvantages too, but overwhelmingly, the advantages of the list class kind of make it more useful than the array class. So lists are a flexible data structure that can grow and shrink, meaning you can add items to them and delete items from them, and that makes them a little more useful than an array. Internally, the list stores its data in nodes, and if you've taken a C++ class, that's a classic exercise where you make your own list class. You make a node that's got a pointer to the next node and a value, and then that node has a pointer in data value and a pointer to the next node, and finally, like the last thing, has a pointer of null. And then later you learn about the vector, and you're like, why did somebody make me do all of that work for? And then you bash your head on the keyboard. But the takeaway there is that to get something out of a list, you have to traverse the list and kind of go on this like scavenger hunt through the computer's memory, whereas an array, everything is contiguous. So that's the downside. So lists can grow and shrink as long as you have enough memory to store all those nodes. But the key thing is that they can grow and shrink, and that they're flexible in size, and that generally makes them more useful than an array. So lists are flexible in size. We can insert something anywhere easily into the list. We can remove things from a list. We can easily search a list and sort a list. We can reverse a list, and we can convert a list to an array. C# collections are great like that. It's fantastic. You can take an array has a toList function, and a list has a toArray function. So you can easily convert back and forth between types of collections in ways that you can't do in other languages. So it's really, really great. Now let's actually look at the list class, how we would use that in C#. So in C# we use what might appear to be a template notation. If you've seen this probably in Java or C++. This is in C#, it's called a generic. But so what's going on here is that when you create a list, you create a list of a particular type, and that particular type is determined when you write your code. But then when you actually compile your code, a specific version of that list class will be compiled that stores that particular type that you specify. So what we're doing here is the T is a placeholder for the type of data that you actually want to store in the list. So T is going to get replaced by whatever type of data you want to store in the list when you go and write your code. So if you want a list of integers, you're going to replace the letter T with an int. If you've got a class, like an image or something, you want a list of images, then you're going to have a list of image, right, in the angle brackets. So the type inside of the angle brackets is going to be specified by you when you write in your code that you need a list that stores a particular type of thing. And again, the angle brackets are in C# and they're in the .NET world, we call that a generic. So let's look at the specific definition of a generic as provided by Microsoft, and then we'll kind of distill that. Generics introduce the concept of type parameters to the .NET framework, which makes it possible to design classes and methods that defer the specification of one or more types until the class or method is declared and instantiated by client code. For example, by using a generic type parameter T, you can write a single class that other client code can use without incurring the cost or risk of runtime casts or boxing operations. What does that mean? Well, imagine we had a list class, and C# has this. They have a class called ArrayList, and it accepts a reference to an object. And imagine we wanted a list of an array list of integers. Well, integers are value types. They store their values directly. They are not references. So if we wanted to have a list of those, we would have to put a box around each one of those so it could be treated like a reference type. That would be called boxing. And then when we wanted to dereference the things in the list or get the things out of the list, we would have to unbox them. that is very, very expensive computationally. That is something that you want to avoid. And generics get us around that. So if we have a list of characters and a list of integers and a list of images, when we go to compile our code, we'll actually end up with 3 separate classes that all basically do the same thing. So our code base will increase a little bit in size, but the speed benefits will be will be great because we avoid that boxing and unboxing problem. So let's take a look at how we would instantiate a list, or how we would use the list class. So the type T, which is T is just a placeholder for the type that we're going to specify when we use the list. Here we're going to use that here. So here we're creating a list of integers, and a list of characters, and a list of images. So you can see that we're still using the same list class, but inside of the angle brackets, we're supplying the type. And when we actually build our project, we're going to end up with 3 separate classes built into our project that, for each particular type. However, the trade-off is that we won't have to box and unbox, and the list performance will be much faster. Also, this arrangement allows us to create a collection that can store any type of data. We don't have to have, we're not bound by, okay, our list can only store this because that's what we wrote it to do. We only have a list that can store integers because that's how we wrote it. It's like, no, now we can defer the specification of the thing that it's going to store until compile time. And that makes this templated notation much more flexible. Now, why don't arrays do this? It's because, well, arrays are a very, very old, very, very primitive type of collection where it's just a block of a chunk of memory that's been reserved, and we're trying to maintain backward compatibility with older languages, or we're trying to preserve the way that arrays are used. We're trying to have a syntax that mimics the way that arrays have always been used. And arrays are being one of the oldest collections, kind of predate templates. So that's why arrays don't really use this syntax, and other collections do. Now, these collections are all reference types. So when we want to create a list of characters, or a list of integers, or a list of images, we can declare our list or our collection, but then we have to go allocate it using the new operator. So here's what the syntax for that would look like. And I like, I kind of like the way it works. I find it to be very readable. So I would read it like this: a list of type integer called ints is, references a new list of type integer. That's how I would read that. A list of characters type called chars is referencing a new list of type char, or a new list of images called images is referencing a new list of images. So that's how I would read that. I would read the angle brackets as of type, a list of type images. So that's how we would create or declare and allocate a list. Now, when the list is created, it's empty. So how do we put things into the list? Well, we can use the add function. That would just put something in the list. It actually would put it at the end of the list. Or we could insert something at a specific position, and that would bump everything else down. So we don't have to worry about shifting elements like we would in an array. We can just append something to the end of the list, or we could insert something at the beginning of the list or in the middle of the list, whatever. Again, that's the flexibility of the list is very nice. So we can either put something at the end of the list, or we can insert something at some position that we specify. Now, what about removing things from a list? Well, we have 2 ways to do that. We can remove a particular item, which we would specify in the remove function. We'd say, okay, remove the number 5 from this list of integers. Okay, boom, the first instance of the number 5 is going to get removed. Or we can remove things by position. So we could say, okay, remove the thing in index 0. All right, so remove the thing at the front of the list, and then the list would kind of shrink. The second thing in the list would now be the head of the list. So we can remove things by position. We can remove things by value, again, which is very convenient. So how do we get stuff out of the list once we've put it in there? Well, there's two ways to do that. We can either use the square brackets just like we would with an array, or we can use the element at function and supply an index. So there's two ways to get stuff out. We can treat the list like it's an array and use the square brackets, or we can use the element at function, which is kind of like more Java-like, and supply an index, and that will retrieve the element at that particular position. So let's take a look at this code right here. So what this is doing is we're going to make a list of integers called scores, and we have to allocate it. So we're going to use it, make it point to a new list of type integer, and then we can add 3 integers to it. Now remember, the add function is going to put the thing at the end. So the 100 will go in first, the 99 will go past that, the 98 will go past that, and then if we execute this statement right here, scores sub 0 is going to be the first thing in the list, which is going to be the 100. So first would be it's going to reference the first thing that was added to the list, because the add function appends things to the list. Now, how do you find out how many things are in a list? Well, lists have a count property. Arrays have a length property. Lists have a count property, which is a little, I don't know, I find that to be a little bit odd, because it seems like most of the collections have a length, but lists have a count. But I don't know, I guess we'll just have to deal with it. So there we go. Now we know how to put things in a list, or create a list, put things in the list, remove things, and access elements in the list. What else can the list do for us? Well, typically, when you have a list, a lot of times you want to sort it, and there are some functions that are built into the list class that will help us sort a list. And we're not going to cover it. I'm not going to cover it in this video, because we need to talk about what it's worth talking about on its own, because we have to talk about interfaces. So you can, a list has a sort function, but in order for that to work, the elements in the list have to implement the iComparable interface, which means that they can be compared to each other. So integers, for example, implement the iComparable interface, because you can compare integers to other integers. So you can create a list of integers and sort it, and they'll all end up in sorted order, and then you don't have to implement your own sorting or algorithm, which is awesome. If you have a particular, imagine you had a list of students or something, and you wanted to compare them. Well, what does it mean to compare students? Do you want to compare them like alphabetically? Do you want to compare them by age or graduation year or GPA or something like that? Well, then you might want to create a separate class that would do that comparison for you. And that is what this second version of the sort function is doing here. So this sort function without a parameter will sort the elements using their internal sort function. And this second sort function here will sort the objects using a class that you provide that will do the comparison based on a particular field or calculation that is defined by you. So there are two ways to sort data. The first one relies on the whatever internal sorting behavior is built into the objects themselves, and the second method here is going to perform a sort based on a class that you provide, and that class is can perform or sort or compare these objects however you want. Now, we're going to talk about that in a separate video about an activity that I put together called Evil Insurance Company, which sorts people by likelihood of death, basically. So you can make class you can make a class that can sort data on arbitrary criteria, but that's a separate exercise. Now, in addition to sorting, there is also some search functionality that is built into the list class. So we have two functions, find and find all. And these functions will return you a list containing all of the elements that matched a certain criteria. Well, how do you specify the criteria? How do you say, okay, I want all of the students with a GPA greater than 3.0, or I want to find all the people who are likely to live past 80 or something like that? How do you specify some way, how do you provide some way as a parameter to these functions that will allow the internal sort, or the internal search function, or the internal find or find all function, to retrieve the elements that you want. And that's where something called a predicate comes in. A predicate is a function that you supply as a parameter, and the predicate will return true or false based on whether or not the object being looked at, or the element in the list being looked at, meets your particular criteria. So in the next example here, what I'm going to do is I'm going to create a list of integers, and then we're going to find all the ones that are positive. We're going to use the find all function to find all the ones that are positive, which means we have to write a predicate function that will tell us if an integer is positive. This is very easy to do. You know, you could do this probably with your eyes closed. Here's a function called isPositive, and it takes an integer called x, and what it's going to do is if x is greater than or equal to 0, we'll say it's positive, and otherwise we'll return negative. Or if it's less than 0, we'll return false, right? So if it's greater than or equal to 0, we return true. If otherwise, we return false. So that's what this single line of code here does. So if x is greater than or equal to 0, we'll return true. Otherwise, we'll return false, right? So this is a function here that will take in a particular integer and return true or false based on whether it's positive or negative. So this function right here is a predicate. This is our predicate function, and we can pass this function in as a parameter to our find and find all functions. So let's create a list here called numbers, and let's just kind of analyze this. Here's a list of integers called numbers, and it points to a new list of integers. And yes, you can actually do this. We can actually declare the elements of the list in line all in one go. So we can declare the list and populate the list in one go, which is nice in C#. So we don't have to kind of declare the thing in the class and then populate it in the constructor. All right, so now what we're going to do is use our find all function and our predicate to pull out all the positive numbers from this list. So what does that look like? Well, there's our list. And remember, we wrote a function called isPositive. We're going to pass that function into the find all function. And what's going to happen under the hood is our list will look at every element that it has, and it will pass it into the predicate function. And if the predicate function returns true, that element will end up in the result set. So 100 will be passed into the predicate function. Is 100 positive? Yep, keep it, put it in the results. Is 5, pass that into the predicate function. Is that positive? Yep, put it in the results. Is negative 12 positive? Nope, don't put it in the results. Is 0 positive? Well, according to our algorithm, it was. So keep it, put it in the results, right? And we're just going to keep going. Negative 8, pass it into the isPositive function. Did that return true or false? Return false. Okay, so don't put it in the results set. And then finally, after iterating over all of the elements in the list, passing them into the predicate function, and if the predicate function returns true, stuffing them into the results set and returning it, we will now end up with a result set, which is another list of integers that just contains the ones that passed the test that the predicate function provided. So that is what find and find all do. Find will just find you the first one. Find all will iterate through the collection, pass each element into the predicate, and keep the ones in the result set that returned true. So so that's pretty nice, right? Because this sort of find all predicate stuff, it saves you a lot of work. It saves you a lot of tedious coding, a lot of tedious looping. Basically, rather than you having to do the looping is now built into the list class, and you just have to provide the predicate function. Now, there's even a slicker way to do stuff like that, like this, using LINQ, that we're going to get to later on. So there would be a way to write a query. We could query this list of integers and get back the positive ones. So this is one way to do it for sure. So the next thing we're going to look at here is something called a lambda expression. And what we've done up till now is we wrote our predicate function standalone and passed it into this find all function right here. But we could have declared our predicate function in line, like right here inside the function call. We could have declared our predicate function right there. So let's see what that would look like. It's kind of a weird syntax, but it's one of those things like once you kind of get used to it and you know it's there, you start using it, you don't think too much about it. So what we're going to do now is rather than passing or declaring a function somewhere else and passing it in, we're going to declare our predicate function right here. So this is the same thing that we wrote before. This is our predicate function, and it's really just it's an anonymous function. It's some anonymous function that takes an integer called I, and it points to, or its body is, so that's the little equals greater than, or I see that as a rocket ship in my 12-year-old brain. So the parameter list points to the body, and then it returns true or false if I is greater than or equal to 0 or not. So what we've done is declared the predicate function in place and passed that in. And that's a little bit cleaner than declaring it separately and then passing the name of the function in. So that this is syntax, I mean, in terms of the result that we're getting, the result we're achieving, this is we're getting exactly the same back as we did before. The only difference is we've just kind of compacted our syntax a little bit and we've declared our predicate in place. So there's no function name here. Right? We're just declaring an anonymous function that takes a parameter called I, which is an integer, and it points to, or its body is, well, that whatever we specify in here, we're going to return true or false based on I being greater than or equal to 0. So that's called a lambda. It's like basically an anonymous function that's declared in place. And you don't really see this, I guess I haven't really seen this in C++, but you do see this in Java with anonymous event handlers. You know, like you create a function that responds to a button being clicked. You just declare it in place. And C# kind of has that same construct. All right, so if we can find everything or find all using a particular predicate, can we remove all using a predicate? Yes, absolutely. What a rhetorical question. So yes, there is a remove all function built into the list class, and we can provide a predicate function that will delete all of the elements that meet a certain criteria. So like, let's say, you know, we've got a list of potential customers, you know, for our insurance company, and we want to remove all the people who are likely to die of smoking. We can say remove all the people who, and then provide a predicate function that returns true for all the customers who are likely to die of smoking or smoking-related illnesses or something like that. So yes, there's a remove all function as well. And again, this is very nice because it saves you the hassle of having to do all the mindless looping yourself. The mindless looping is now built into the collection class itself. Now, one thing I maybe should have talked about, I don't know, just iterating through a list. Maybe if you've got a list of things and you just want to blast through it and print them all out, this is where a for each loop really works great. So all you have to do is just type the word for each, hit tab twice, and it will stub out a loop for you that you can use to loop through your collection. And it would look something like this. So imagine that we had a list of integers called scores, like we did in our previous example. For every integer n in scores, and then now you have, for every time this loop iterates, the particular element being looked at will be referred to as n. So what we're doing here is just accumulating or adding up the sum of a list of integers. I guess now what I would do, being like loving extension methods, is I would go put an extension method on the list of int class and put this in there. So then I could just say, you know, I could have a list of integers and just say, you know, list.sum, and it would do it all for me. I'd use an extension method to bolt this kind of functionality onto the list of integers. So again, that's all of these collections support for each loops, just for each tab, and then specify the name of your collection here. And you'll be able to iterate through your collection easily. The only time that this doesn't work well is when you need the index for some reason. You're trying to find the position of something in the list. when you use a for each loop, you lose the index. So if for some reason you've got a situation where you need the index, then, or if the index matters, then use a for loop. If the index does not matter, use a for each loop. Also, you cannot modify a list while you are iterating over it. So you could not, and again, this is where remove all really comes in handy, or remove comes in handy. If you try to delete something from a list while you're iterating over it using a for each loop, that will blow up in your face because you're kind of corrupting the list iterator. So just be aware of that. So if you just want to blast through a list and examine everything in it, then for each loop is the way to go. If you need a specific index, then use a for loop. All right. So thoughts on lists. I use lists more than I use arrays, just because they are more flexible and I can treat them like arrays using the square brackets. If I ever have if I'm ever in a position where I actually need to have an array for some reason, you can just say whatever list dot to array, and it will return you an array version of that list. It'll just sort of pack everything into an array and return it to you. So awesome, great, off you go. But the performance penalties for using a list versus an array are real. So let's look at this little thing I found on Stack Overflow. An array of type T versus a list of type T can make a big performance difference. I just optimized an extremely nested loop intensive application to move from list to arrays on .NET 4.0. I was expecting maybe 5 to 10% improvement, but got over a 40% speed up. No other changes than moving directly from list to arrays. All enumerations were done with for each statements. Based on Mark Gravel's answer, it looks like a for each loop with list T is particularly bad, right? So arrays, even though they're kind of old school and simple, because the items are all contiguous in memory when you are iterating over them, that iterator, the calculation of where the next thing is in memory is very, very fast. Whereas with a list, if you are trying to access things in a large list, you have to go on that scavenger hunt following the pointers through memory, and that can be very time intensive. So if you have something that is particularly performance intensive and flexibility is not a requirement, the array is something that you may want to go with. Finally, one very, very important thing, and if I were going to interview people for a C# job, I would ask this question, or something. I would hit this topic. Never, ever, ever use the array list class. It is a legacy collection, and it's based on sort of the Java list class that takes an object. It's a very early type of collection. And remember, I talked about how template notation allows you to bypass this penalty that you incur called boxing and unboxing when you put things into a list and take it out of the list. Array list suffers from all of those problems. The array list was built into the language before the generic syntax was added to the language. So an array list is an early type of collection that suffers from a lot of performance drawbacks or deficits. So never, ever, ever use array list, because you will incur the boxing and unboxing penalty when you put things into the list and take it out. You should always, always, always use a list of type T. So that's, I guess that's all I have to say about the war in Vietnam. I didn't realize that there was so much to say about lists, but they're very useful. The way they're implemented in C# is great, with the find all, remove all, being able to iterate over them with for each loops. They're great, and I've never really run into an application that was so performance intensive that I really had to fall back on arrays. So there you go. But those are C# arrays in a nutshell. We'll be doing some exercises with those using the find all and remove all, and then we'll be looking at some other collections as well.